Hi, I'm Scott Mack, a DFT Manager at Marvell. I'm part of the Marvell team that's developing custom XPUs for hyperscalers. As you probably know, computer architectures of the past largely focused on a single technology, fitting the logic content into a single die of the targeted technology's many available die sizes. In that design environment, a DFT engineer like myself focused on instrumenting the design content to enable manufacturing test of an individual die to a known good or bad status. These known good die then move forward to single chip module assembly and test. But as XPU architectures have evolved, their size and complexity has increased dramatically. Moving to the next smaller technology node has been a straightforward way to continue to fit into a single chip module while increasing the speed and compute power of the design. However, with each new technology node, the cost is now increasing, so it becomes imperative to put even more content and capability into the XPU. So to meet rising costs, complexity, and size demands, newer XPU architectures have begun splitting functions from the primary die into one or more satellite die of the same technology node, or even older technology or trailing technology nodes as a cost savings measure. This leaves in the primary die the core workload logic. Then this collection of primary and satellite die is assembled as a multi-chip module or an MCM. While each die mounted on an MCM is a known good die, just mounting a collection of known good die on an MCM does not make it a known good MCM or module. Thus, the challenge the DFT engineer faces with MCMs is architecting and implementing a test solution that encompasses the test architecture and structures of all the individual dies that make up the MCM to test the MCM to a known good module status. We've been working closely with Siemens and our other partners to meet this MCM challenge.